All right, I guess we got two people so far. We'll wait a couple of minutes. I know it's early, especially if you're home. Everyone's thinking, "Oh my God, do I really have to get up this early?" But of course, when it's online, you don't have to get up as early as usual, which is kind of nice. But we'll carry on in a couple of minutes. I was double checking my notes, and it looks like the last thing we did, or we left off with the sampling distributions of the proportion in chapter 8. And when that's done, we can dive into chapter 9, which is actually the last chapter of the course. So, we're zooming along here. When we get back, though, we only have 2 weeks, so we have to stay on top of it. So, what's different here with the sampling proportion is we're actually doing this for the first time. We're considering proportions rather than means. Luckily, we're still using the normal distribution. So you can still use these guys. All right. And that hasn't changed. But in chapter 9, we're going to be introduced to another new probability distribution for the first time. And then, we'll do it for different reasons. But anyway, we'll still be using the normal. That never changes. But sometimes we'll also use other distributions as well. All right. So now, I don't know. It's possible that some of you have never done this Zoom session before. So what I'm going to recommend everybody do is that you mute your microphones. Although I think I can do it here if it comes to that. Not because I don't want to hear what you're saying, but if it's not muted, all the background noise will come through. So if, for example, your dog starts barking or something, we'll all hear it. So if you do want to say something, though, you can unmute it, and then you can ask your questions if you really would like to ask questions. There's also other things you can do, like there's a chat up here. You can actually type questions in here if you want. And also, I think, although I don't know how it works, there's a way you can raise your hand. Somewhere in all of these controls, there's a way that you can actually hit an icon that has a hand. It looks just like this. I don't think that's necessary. You can just go ahead and turn on your microphone and just ask if you want. I'm so, I'm so technology challenged. It's unbelievable. So, other than that, I think we're in pretty good shape here. So, of course, this is going to be recorded. It is being recorded. It says it right there somewhere. And that means that you can watch this later on if you want to. Now, I'm not positive that we can fit this into Blackboard. I think it has enough room. I've had issues in the past doing that, but even if that is the case, I do have my own YouTube channel, which I used extensively during the COVID. And you should be able to find it without any difficulty. I'll put it in both places just to be on the safe side. I'll also go ahead and create a playlist, it's called, where we can keep our videos to make it easier to find them. So what you would have to do, see this A here, that's how I know it's mine, Dr. ACA. Or if you type my name, it'll come up anyway. So then you would go in here and in the playlists, you'd find the one that you're looking for. Okay. Let's see. If you go to, oh boy, I'm starting to forget how this works. It's been a while since I needed to make a recording. So here's your videos, and that's fine, but I would still like, there they are, the playlists. And so yeah, you'll be able to find yours. So it shouldn't be too difficult. All right, anyways, let's get back to this. Anyways, I started to say, we left off here with the sampling distribution of the proportion. So far, everything we've done was related to the mean. What is the proportion, by the way? Well, think about this. Suppose I wanted to know what proportion of people, of Starbucks customers, drink decaf. Okay, obviously they need to know what proportion of their customers are drinking decaf, so they know how much to produce. So we define the proportion as the number of elements in a population or sample divided by the size of the entire population or sample. Of course, most of the time we'll be working with samples. So, here's an example on top. I wrote last time I did this online. If 4 out of 46 students are left-handed, the sample proportion is simply 4 to 46 or 8.7% or 0.087. That's all it is. Okay, so this is how we'll define proportions. And it turns out that proportions actually follow the binomial distribution. But based on the normal approximation to the binomial, we can use the normal distribution to come up or represent the properties of the proportion. Okay, so that concept that we learned in chapter 7 turns out to be quite important. The normal approximation of the binomial is going to be very useful in cases like this, where we can use the normal distribution to represent probabilities for the proportion. Whereas if not, we would have had to use the binomial distribution, and it would have been very time consuming. So letter P, lowercase p from now on, will be used to represent the sample proportion. And surprisingly enough, in the book, they're going to have us use capital pi or the population proportion. And it makes sense because pi is the Greek equivalent of p. Now, by the way, you notice I'm using this very cool piece of technology here. It's a tablet. It's attached to my computer, and I'm literally writing on the screen right now with a little marker. Okay, there it is. Okay, so it's very cool. It's like having a little second monitor here. It's very easy to see what I'm doing. I can write on it. It's very rare that technology works this well for me, but this one does seem to be working. So anyway, the capital pi is the population proportion. The lowercase p will be our sample proportion. And when we conduct tests, we'll, of course, be using the actual sample proportion to estimate properties of the population proportion. So therefore, yes, and as it says here, since each element of our population or proportion has a certain characteristic or else it doesn't, you can see why proportions actually do follow the binomial distribution. But it's usually easier for us to use the normal approximation to the binomial than the actual binomial to calculate probabilities for proportions. Okay. Now, specifically, n and pi, by the way, you might remember from when we were doing the binomial distribution, we used the lowercase pi to represent the probability of a success. And of course, n is the sample size. That's always been the case. So it turns out that this process works best when two conditions are true. N times pi is at least 5. And n times 1 minus pi is also at least 5. Okay. Now you can still use it even if these are not both true, but the accuracy will be highest when both of these conditions are met. Now, we're going to assume throughout this chapter that both of those conditions are met. So we'll just go ahead and always use the normal distribution for these probabilities. But we also have to be aware that P, the sample proportion, has its own unique set of moments. In spite of it being normal, it still has its own unique set of moments that we have to be familiar with. For example, the expected value of P is equal to pi. Okay. I'll give you a chance to write that down. And then, like in chapter 8, the variance and the standard deviation depend on the size of the sample relative to the population. Okay, so let's just quickly remind ourselves that in chapter 8, this earlier in this chapter, large means sample is greater than 5% of the population. Or we can rewrite that as the ratio is at least 5%, more than 5%. Small means the opposite. Oh, look what I did. There's a typo here. Actually, it's not technically a typo since I'm writing by hand. Okay, now we're all set. So I just want to quickly remind you the way, I mean, since we had a test and, it's been a while since we thought about this, but the cutoff point between the two is 5%, small and large. And you notice it's not an absolute value. It's relative to the size of the population. So that's what we're really trying to capture here. Small means less than or equal to 5% of the entire population. Large means greater than that. It doesn't actually matter how large the sample itself is. It could be huge, but if there's a massive population, then our sample could still technically be small relative to the entire population. So why am I reminding you of this? Because if you recall that earlier in the chapter, the moments that we saw, at least the variance and the standard deviation depend on the size of the sample relative to the population. So that will be the case here as well. So let's take a look at the variance and the standard deviation for a small sample. Okay, so remember, this is for small. And I just want to put in parentheses, in this context, small means relative to the population. Okay. It's an important point. All right, well then what about large? Well, you remember we introduced this term called the finite population correction factor. The same thing will happen here. When we have a large sample, we'll need to use the finite population correction factor. Yes, there it is, our old friend, the finite population correction. Okay. Now you recall from earlier in the chapter that once these numbers have been established, you can just go ahead and use the normal distribution. In other words, you can go to your calculator and just use normal CDF to come up with whatever probabilities you might need. Now it turns out that I very conveniently draw a nice little chart here. Although I see there's a typo, and let me fix that. Oh, there isn't. Yes, there is. There we go. Okay, so if you want, you can use this to keep track of which is which, but just be aware that on the small side, we do not use the finite population correction factor, and on the large size, we do. And again, keep in mind, the whole point of this finite population correction factor is to reduce the size of the variance and the standard deviation. If you look at this term very carefully, you'll notice that capital N minus lowercase n over n minus 1 is guaranteed to be less than 1. All right, so finally, after all that buildup, we can do a problem. So here we go. US government data show that 15% of Americans are retired. Fine, that's the population proportion, 15%. What we're going to do is randomly sample from the state of New York. For some reason, let's say they think that maybe that proportion rather, is higher in New York State than for the rest of the country. So they take a random sample of 200 New York residents to determine what proportion is retired. Okay, so and by the way, here they're specifically interested in 20%. They want to know if the number has reached 20%. So what is the probability that that's true? Okay, in other words, given that we have this population measure of 15%, what's the probability that in New York State, 20% or more of the people are retired? Now, of course, we could just go ahead and look at all the residents of New York State and find out the answer, but that would take a very long time. Here, we can just take a simple random sample of 200 people and come up with a very good result. The first thing we always do in these cases, of course, is to come up with our moments. So now, given that we were told that the population proportion is 15%, the entire country, the number is 15%, that means that we would expect that in New York State, the same thing would be true. Okay, so the expected value is equal to 15%. Now, what about the other values, the variance and standard deviation? Well, for one thing, we can be pretty confident that even though we were not told the exact population of New York State, a sample of 200 is pretty obviously very small. In fact, 200 is 5% of 4,000. So unless you really believe the population of New York State is less than 4,000, we're in solid ground, assuming here that the sample that we've chosen is small. Okay. Oh, it looks like I did look it up. I'd forgotten about that. 19.45 million. So I think 200 out of 19.45 million qualifies as small. So we're going to use these two formulas. We have sigma squared p, the variance in the sample proportion, is pi times 1 minus pi over n. And you can see that works out to be 0.00064. And then the standard deviation is simply the square root, as it always is, which is roughly 0.02525. So we have our moments. Now, what we want to do is calculate the probability that our proportion is greater than 20%. Okay, so let's check this out. Now, by the way, this is something we see in every chapter where we discuss the normal distribution. If you're going to use tables to do this, you have to have a conversion formula. Okay, the tables are based on the standard normal distribution. So for this particular case, this is what you would have to do to convert your sample proportion into a standard normal random variable. If not, you can just use your calculator, the way we're used to seeing it, normal CDF. But if you did choose to use the tables, you would have to go through this step first. Now in the slides, I'm assuming that that's what you're doing, but I also have the instructions for the normal PDF as well, normal CDF rather. Okay, so you can see if you're not going to use the tables, you don't need to deal with this part. But if you're going to use the calculator, here's the part you do have to deal with. So as usual, we pick second vars. Number 2 is normal CDF. And since we're interested in the probability that P is at least 20%, the lower limit is 0.20, the upper is infinity. We've just determined, oh, by the way, this is equal to this case, right? By the way, some books, I just want to mention this too. Let's go back to the moments for a second. Some books use the notation mu p just to reinforce the idea that it means the same thing. It's the mean of the sample proportions distribution. Okay, so it is the same thing. Okay, and then this is exactly what we calculated. This, of course, is what we were calling sigma p. Okay. And so you plug in those numbers and you'll get your probability is 0.02384. Right? So I'm assuming that even though you might be home or in your room, your calculator is right in front of you because you're not supposed to go anywhere without it. So why don't you pop out the old calculator and confirm that this is correct? Okay, I'll give you a minute to catch up and then we'll that's it for chapter 8, I just realized. So then we can start something completely new, which in the first half will be based on the normal distribution, and in the second half, we'll introduce the mystery distribution. All right, here we go. So I think we're done. Oh, also, I just want to point out, I'll be posting this version of the chapter 8, the one with my handwritten notes, as well as the regular one, which is already there. So that way you won't lose anything I've written here. So if you somehow neglected, you're unable to take notes or whatever, it's all right here. All right. So that's that. All right, let's get this out of here and let's go to 9. Now, 9 is a completely new topic. We're not exactly calculating probabilities here. Yes and no. What are we trying to do here? Well, we're introducing the notion of confidence intervals. Now, you recall from day one that we normally don't have access to the entire population, or at least we could maybe potentially get all the information in an entire population, but it would be very time consuming. So we usually instead rely on samples. So what that does, though, is that it means we're using an estimate from a sample to represent the properties of an entire population. And we know that that introduces a certain amount of uncertainty. For example, we know that we've often used X bar is used to estimate U. Even if we are careful with our samples and we choose them very well, every sample mean is likely to be different when chosen from the same population. So that means there's going to be some uncertainty associated with the accuracy of that X bar. Like, for example, if I choose X bar, a sample of people, and I ask them how old they are, let's say that X bar turns out to be 29.2. That's good, but the problem is we know that the underlying population mean is likely to be different from that. The question is how different. And so the confidence interval lets us come up with a range of values within which we think the population mean actually falls. And that gives us more information about the population mean. We not only have an estimate of the population mean, but we have an estimate of how much uncertainty there is associated with that mean. So, for example, what if I told you that we did this with gas prices, and I told you that 95%, the 95% confidence interval for the mean gas price in the US is, and this is, first number is often called the lower limit, and the second one is the upper limit. So what it's saying is that, yes, our best estimate is 309. By the way, this implies that must have been 309. Why? Because it's halfway in between. Sorry, not 309, 319. What you've got here is 319. And then what we've done is we created what's called a margin of error. Which is 20 cents. So this lower number is actually X bar minus the margin of error. And this number is X bar plus the margin of error. This is our estimate. This is what's telling us how much uncertainty there is. In other words, if we drive around and visit various gas stations and note that they're all slightly different, this gives us a sense of how much different they're likely to be from each other. So that while our best estimate of the gas price, the mean of all the gas prices is 319, we are highly confident that the true mean is somewhere between 299 and 339. For example, we may have inadvertently gone through very expensive neighborhoods, and we may have inadvertently chosen the most expensive gas station, or it may have been the other way around. So we know that 319 is not a perfect estimate, but we know that it's pretty close. It should be roughly within 20 cents of the true population mean. You can see how that's much more useful than just knowing the X bar. It takes more time and more information to construct a confidence interval, but as you can see, it's also potentially much more useful because the 319 by itself doesn't give me any sense of how much there might be, how much difference there might be from one gas station to the next, whereas the interval does. Now, yes, so I did mention this. The 299 is called the lower limit of the confidence interval, and the 339 is the upper limit. But where did that come from? It is the mean, the sample mean, plus and minus that margin of error. And by the way, the margin of error is the tricky part. That's going to be the complex part. It is the most difficult part for us to estimate. And it also depends on the circumstances that we're drawing samples under. All right. So now, Now, here's a quick and easy example of this. What if somebody wanted to know how long does it take you on average to get to school every day? And you say, well, you know what? I've been writing it down and I've discovered that the sample mean is 30 minutes, but I know perfectly well that some days it's quicker than that and some days it's slower than that. Why? Because traffic is different every day. And sometimes the weather is crappy and sometimes it's not. So what I'm going to do here is write down how long it takes to get to school every day. And what I've discovered is that 30 minutes is the average, but the majority of the time, roughly 95% of the time, it's actually going to be somewhere between 25 and 35 minutes. So what I've done is I've actually constructed a confidence interval. Now, there still might be the occasional day where it's less than 25 because, oh, the traffic is unusually light. And then maybe it's more than 35 on other days because the traffic is usually terrible or else the weather is really nasty. But the majority of the time, it's going to be somewhere between 25 and 35 minutes. So the 30 minutes is a sample mean. And the formal name of this is a point estimate. The word point means it's a single value. So now we're getting some deep waters here. And now the range from 25 to 35 is known as a confidence interval, specifically a 95% confidence interval, because only 5% of the time was our commuting time either less than 25 or more than 35. Now you do this all the time. It's, whenever you say give or take, the words give or take indicate that you're using a margin of error. Let's say that you tell somebody, I'll be at your house in an hour, more or less, or give or take 10 minutes. Well, what you're actually doing there is constructing a confidence interval. You're telling somebody that you'll be there within between 50 and 70 minutes. That way they know, if they're planning, let's say they're cooking something, they know how much time to allow for you to get there. It's especially important this time of the year. You don't want to be telling them you're coming in an hour and then you show up 3 hours later. No. But by giving that plus and 10 minus 10 minutes, you're actually creating a confidence interval. I'm sure we do this all the time. Or if you're trying to give somebody directions, how long does it take to get to Brooklyn, let's say? Well, you don't know exactly, but you give them a rough idea and you give them a range of possible values. That is a confidence interval. All right, so yes, and this is obviously very helpful information because it provides a range of uncertainty. We don't usually know the exact value, but we can get a sense of what might happen by creating a confidence interval. Now, in this, by the way, here we're going to be constructing, at first, we're going to construct confidence intervals for the population mean. And under some conditions, we'll be able to use the normal distribution. But then all of a sudden, we'll run into cases where that's not true any longer. In other words, it will no longer be possible to use the normal distribution. What do we do then? Okay, well, if this was, let's say, the distribution we're going to introduce later on in this chapter was introduced in, I think, 1906. So if we were trying to do this in, let's say, 1899, we'd be in trouble because we don't have another distribution to take the place of the normal. The new one that we'll be looking at later on proved to be quite important. And we'll get to that in the second half of the chapter. Now, we're going to introduce just a few key terms here. These are not critically important, but you should be familiar with them. When you see the word point estimator, they're talking about a formula. For example, write out the formula for X bar. This is called a point estimator. It is an estimator of mu. It's called that because it's a formula. You notice how it's not a specific value. It is basically a technique for finding an estimate of mu. But once you come up with an actual number, suppose that X bar turns out to be 3. This is now known as a point estimate because it is a specific constant. Okay, so let's say that is my best guess for the average price of gas in, let's say, Mississippi, where prices are much lower. That is an estimate. The formula, though, that I use to get there is called the point estimator. Okay, so it's a very subtle distinction. But in statistics, everything has a name. So I just wanted to mention them. We're not going to focus on this too much. But the reason why we're bringing it up now is because we want to distinguish it from the confidence interval, where instead of having a single number, we have a range of values. So that changes everything. And so the names we'll use are a little bit different. An interval estimator is a formula that will be used to calculate a range of values for a population parameter, a specific probability, which reminds me, I want to review one more time these words. Parameter is simply a fancy name for population measure. That includes mu, sigma squared, and sigma. Those are all considered to be parameters. Statistics are sample measures. That would include X bar, S squared, and S. All right, just so you don't forget what those words mean. Okay, so an interval estimator is the formula, which we'll be introducing in a second, that lets us calculate a confidence interval or a range of values. The actual result in this interval, and just to remind you, such as the example we had a few minutes ago, 299 up to 319, is known as an interval estimate. The word estimate means it's the numerical values as opposed to the formulas, which we haven't introduced yet, but we will. That's called the interval estimator. Okay, or versus et. All right. Okay. So it sounds very bizarre and abstract, but believe me, your calculator will be hugely, and I mean hugely helpful in this chapter. In fact, here's the rule of thumb that you'll find as you go forward in this class and the one that follows. The more complex the material is, the more help the calculator will give you. Okay, so that's kind of nice. By the time we're done, you'll be experts in calculating these confidence intervals using your calculators. All right, so let's see. If, let's say, we've used some calculations to determine that the population mean is between 5 and 10 with 95% confidence, then this is our interval estimate because those are the actual numbers. The formulas we don't see here, but whatever they are, they're the interval estimator. Okay. All right. Now, here's an interesting side note. We usually construct confidence intervals at 3 different confidence levels. You see, I've been using 95 as our example, but most of the time we'll either use 90, 95, or 99. In fact, in this chapter, we're only going to use 90, 95, and 99. Most of the time in practice, it's 95. It's just people are comfortable with it. It makes sense to everyone. 95 is a very popular choice, but sometimes it's not exactly what we need. And so we'll lean on or use 90 or 99, but that's it. We're not going to get anything crazy like 72 or 64. That's pretty much going to be those are the 3 we'll use. I'll just make a note up here. We'll use 90%, 95%, and 99% confidence intervals. Most of the time, 95% is used. Now, you might ask yourself, well, what difference does it make? Which one we use? Well, that's a very good question. So what's happening here is that something interesting is taking place. Oh man, this PowerPoint is actually disobeying me. I keep turning this stupid thing off and it keeps not doing what I tell it. All right, here we go. So as far as that goes, a higher confidence level means that they're, let's see, have a higher, I'm trying to think of a good way to explain this. We have more certainty that the true population parameter falls within the confidence interval. But in order to achieve this, we must include a wider range of values. Okay, so let me give you a quick example of this. So in other words, if you end up choosing, let's say 99%, that means we have even more confident than ever that the interval contains the population parameter that we're studying, like the population mean, for example. But that means we have to widen up the interval to include more possible values. So let me show you an example of this. Going back to the example of commuting. Okay, 95% confidence interval contains the values. 20, what did I say? It was 25 up to 35. Then a 99% confidence interval has to include more unusual days in it. You know, days where the commuting time was either shorter or longer. Maybe that it makes it 22 up to 38. Okay, in other words, the margin of error, the mean in both cases is 30. But with 95% confidence, the margin of error is 5 minutes. But with 99% confidence, margin of error is 8. And now, why is this happening? Because now you're including a wider range of possibilities. So now you're including 99% of the times that you've driven to school. And you must now include some of those oddball days where you only needed 22 or 3 minutes to get there, or some of the really bad days where it took even longer. So increasing that confidence level is going to also increase the number or range of values that you must include in your intervals. Okay. So if we now knocked it down to 90%, oops, the corresponding 90% confidence interval might only include the values, let's say 27 up to 33 with a margin of error of 3. Okay, because now we don't need to be quite so confident. We're not going to include some of the shorter days and some of the longer days. So instead, we end up with a range from 27 to 33. So the point of all this is that the more confident we need to be in our results, or the less uncertainty we want, the wider will be the range, or let's just put it this way, the greater will be the margin of error, and the wider will be the range of possibilities. In other words, the lower will be lower limit, and the higher will be the upper of our confidence interval. Now, once you see a few examples, this is all, again, very abstract at the moment, but once you do a few examples, you'll see it right away. We'll do several examples with 90, 95, 99% confidence. Okay. And then you'll see that we'll compare them to each other and you'll see what this is all about. Right now, you're like, what's going on here? It's very confusing and complicated. But you'll see when we get to that point that this all makes perfect sense. Okay. Especially just before a holiday, you're like, what are we doing here? This is so abstract. But like so many times in statistics, it starts out seeming frightening, and then before you know it, it's the simplest thing. Okay. It just takes a little getting used to. All right. So I think we're almost ready. So in the most general possible terms, confidence interval means you've got some point estimate, which for our example, for estimating the population mean, what you're going to have here is X bar plus and minus your margin of error. So that's all this means. X bar plus and minus your margin of error, just like when we had the commuting times and the gas prices, it's the same idea. Okay, and that's what it says in the next slide. For the population mean, we're just going to have X bar plus and minus the margin of error. The margin of error is the uncertainty. The uncertainty using X bar to estimate mu. And by the way, that changes in every case. In other words, in some cases, the uncertainty is actually quite low. In some cases, like, let me give you a quick example of this. What if you are not a commuter, but you're living on campus? Well, the margin of error for how long it takes you to get across the campus is going to be very, very small. I mean, what could change from one day to the next? Maybe the weather. But when you're commuting, a lot of things can go wrong or right. So the range of possibilities will be very wide for driving versus walking across the campus from your room, where at most the margin of error might be a minute or two, because, some days you walk faster than others, and some days it's raining and it slows you down a bit. But so with commuting by car, the margin of error will be quite a bit larger than commuting by foot. Okay. So again, with this example we've been using, 25 to 35, the point estimate is, or X bar is 30 minutes. And the margin of error is 5 minutes. Okay. By the way, you can always tell what the point estimate is because it's the average of these two. So if you weren't sure, if you took the average of these two, let's see that it's 60 halves over 30. The margin of error can be calculated very easily. Take the upper limit and subtract X bar. You could also do the same thing by adding X bar to the lower limit. Okay, there we go. Now, as far as this goes, when we're dealing with the population mean, there's only two cases we could potentially encounter. Either we know the population standard deviation or we do not. That's all we have to choose from. Yes or no. So we'll start with the first case, sorry, where it is known. And the reason why we're doing that is because that enables us to use the normal distribution. Okay, when we get to the second case where this population standard deviation is not known, that's when we have to introduce the mystery distribution. Okay, so right now we can continue to use our old friend, the normal distribution, with the assumption that sigma is known. Now, by the way, it'll say that in the problem. You do not have to figure this out. It'll just say right in the problem, it is known or it is not. Okay. Usually, though, you can assume, let's say it doesn't explicitly say the words, we know the population standard deviation. The way it works is if, let me just add this in here. If the sample standard deviation is given in a problem, you can assume that sigma is unknown. So that would be a clue. Even if it doesn't specifically say the words, the population standard deviation is unknown. But if they give you the population standard deviation, then clearly it is known. All right. So just to be in the safe side, just be careful. Don't assume the population standard deviation is known unless it explicitly says so. If instead they give you the sample standard deviation, it's because they don't know the population standard deviation, because otherwise there's no point in calculating it if you know the population standard deviation. Okay. All right, here it is. Oh my God. Well, in a way it looks scary, in a way it doesn't. This is the formula we'll use, and you can see this whole term on the right-hand side is what we're going to call our margin of error. But there is a very strange, mysterious new term in here which requires a significant amount of explanation. This thing. By adding that subscript alpha over 2, we've changed the meaning of this term. All right, so we're gonna need to do a little detour right now and understand what this term means. It's sometimes called a critical value. It's sometimes called a z-score because it's based on the standard normal distribution. Our job is to find it. And then we also have, all of a sudden, I've sneaked in here, alpha. What does that do? So that's why we need some explanation. Now, the rest of it, you know what it is. Sigma, this is the population standard deviation. And of course, n is the sample size. Nobody's forgotten. X bar, of course, is the sample. All right, so what we need to do now is step aside and talk about z alpha over 2. So I'm going to start by drawing a picture. Oh, by the way, I just want to mention, it shows you here in the slides that the term on the right is called the margin of error, as we can guess. Got a point estimate, plus and minus a margin of error. It's always the way it works. So here it happens to be this term. But there's a couple of other things we need to be introduced to. So I'll give you a second to catch up. See, this one of the negative things about being online like this is that I can't see what you're doing if you're caught up or not. So I'll give you a second. In fact, I can't see anything. You're all camera shy today. I see that. All right. So this is the margin of error. Now, what about these other terms? Oh, I didn't realize I could not. Look at that. All that space I was wasting showing myself. All right. So the critical values, as I've said, is or z-score is z alpha over 2. This piece has its own special name too. This part is referred to as the standard error. That terminology will come in more handy in stats 2, but it's good to be introduced to all these terms now. And then this alpha is the level of significance. All right, so we're going to see what that's all about in a second. All right. Now, with all that being said, our first job is to figure out what this critical value is. So here's how this works. This is directly related to the confidence level that we're choosing for our problem. So formally, we're going to define 1 minus alpha as the confidence coefficient. And then 100 times that will be called the confidence level. What does that mean? All right, I'll show you an example on the next slide. All right, so suppose we're interested in 95% confidence interval. Well, that means that 95% equals 100 times 1 minus alpha. So let me show you that in the next slide. So for 95%, so remember we said here, this is our confidence level. We set that equal to 95 because that's what we're interested in. And then if you notice, I just did a lot of algebra and all of a sudden, ooh, wait a minute. So alpha equals 0.05 implies that we are constructing a 95% confidence interval. Now, if that's the case, what would the value of alpha be if we were constructing a 99% confidence interval? Well, for 99%, 100 times 1 minus alpha equals 99, and then we go through all the algebra, and we'd end up with 0.01 is alpha. And I'm sure you can figure out that for 90%, you would have 100 times 1 minus alpha is 90 rather, and that implies that alpha is 0.10. Notice I skipped all the algebra, but so those are the only 3 that we're going to use in this class. 95% means alpha is 0.05, 99% alpha is 0.01, 90% alpha is 0.10. All right, now still, that doesn't tell us how to figure out z alpha over 2. All right, so I'm going to draw some diagrams here to help us with this. So let's say we're dealing with a 95% confidence. What are we really trying to do? Here's the normal curve. What we need is to find 2 values under the standard normal curve such that alpha over 2 is in each tau. And in the center, we have 1 minus alpha. So with 95%, we have alpha is 0.05. Alpha over 2 is 0.025. So therefore, this is 0.00 z subscript 0.025 because 2.5% is in the right tail. Now, because of the symmetry of the distribution, this is negative z alpha over 2, which means you have 2.5% in the left tail. And the center area is 95. So that z-score or critical value is a number which separates the upper 2.5% of the distribution from the lower. How do we find that? What value does it have? All right. Luckily for us, the calculator is ready to help us with this. So I've put the instructions here. Let's start with 95%. So here's what you're doing. In order to find this critical value, keep in mind that if the right tail has an area of 0.025, everything else below it has an area of 0.97. So you're going to take out your calculator, which you finally get to get your hands on it. Go to your second vars, which we know by heart, but we're going to use for the first time function number 3, INV norm, which stands for the inverse of the normal distribution. The area is the 0.975 here, because when it says area, it means the area below that point, okay, to the left of that point. That's the way it's been set up. Now, by the way, if you have the TI-84CE, I didn't mention this in here, but there's another option in here called tail, which is set by default to left. So that's the left area. You have the option of switching that to right and asking it for 2.5% if you want, but only if you have this particular calculator. Okay. So if you have it set on left, the area you're looking for is 0.975. If you have it on right, the area would be the 0.025. These do not require any explanation because this is the standard normal distribution. And it turns out that the number is approximately 1.96. That's our critical value. So what that implies is that the probability that z is less or equal to 1.96 is 0.975. Oh my God, what a nightmare this is turning out to be. No, it is. You'll get used to it very quickly. Now, as far as the lower, now remember, this is a confidence interval. We need, if you recall, let's go back to my original graph. We need to know not just z alpha over 2, but negative z alpha over 2. Well, luckily for us, because of the symmetry of the distribution, we don't have to think about anything. Watch this. Because of the symmetry of the distribution, this one must be negative 1.96. Okay, so you only need to look up one of them. Now, by the way, if you wanted to, you could have looked up the smaller one, the negative z.025, and then use symmetry to come up with a positive one. It doesn't really make any difference. So that's the number that we'll use in our formula. Therefore, z alpha over 2 is plus or minus, these are 196. That is really the only tricky part in this confidence interval formula. The critical value, or z-score, as they're often called. Now, by the way, all of this will come in handy in chapter 10, which you will not see until the spring. But when you get there, you'll remember this day and say, you know, I remember learning about this stuff just before Thanksgiving. Wow, this is a lot to do just before our vacation. But no, that way when we come back next week, it'll all be very, you'll understand it pretty well. Now, what I'd like to do is show you how this would work for the other two possible values. 90, this is 95%, don't forget. What about 90 and 99? All right, let's find out. Actually, I've got one of them right here. Let's jump ahead. This is for a 90% confidence interval. That means that 5% is in either tail, 10% total. It means 90% in the middle. So what I'm going to do then is recognize that if you're just looking at the right tail, 5% is in the right tail. Everything below that is 0.925. So area got changed from 90 to 95. I'm using the same technique, second vars, 3 INV norm, but now I've got one, actually I'll put it up here, 1.645 and negative 1.645. Ooh. So the only thing we changed is right here to go from 95 to 90. And then one more, 99. What do we do about that one? Well, that's going to indicate 99% in the center, 1% total in the two tails, or you could think of it as, let's get this out of here, 99%, sorry, 1% total between the two tails, 0.5% in either tail. Okay, so let's see, here it is. So half of 1%, by the way, is 0.005. Don't get confused there. It's easy to make a mistake without. That leaves 99% in the middle. So now what about this area? By 0.005 in the right tail, everything to the left of that must be 0.995. And that's where this is coming from. And you can see the final result is approximately 2.576. That makes this negative 2.576. Now, what's good about these is you can actually memorize these if you need to. If you're really like, oh my God, I'm so confused, I don't know what to do. By the way, again, after a little practice, you'll be fine with this. But what I'd like to do is put together a little chart that summarizes all this. So what we'll need is confidence level Z alpha over 2. There we go. And so that's all of them. Those are the ones we'll never run into any of the others, not in this class. Okay, so what we need to be able to do, though, is reproduce these ourselves with the calculator. You don't want to depend on memorizing these, but if you do memorize them, that's awfully, awfully helpful. Now, what's coming up next is an example. Okay, but the reality is it's going to take a while to get this thing set up. It's already 9:37. I think we got plenty of work done here. So I think it might be a good idea to stop right here. And then this way, if you want to watch the video, again, you may. And if you want to read through these slides, remember, I'm going to post this part separately. Chapter 9 is already in Blackboard, but this one, I've relabeled it with notes 11, 21, 23. So you know it's what we did today. And that way you can go back and revisit this and make sure you understand it. And when you get back, well, we'll run through it again quickly to make sure you haven't forgotten anything. And then we'll dive into the examples. Then we'll introduce the mystery distribution. Something you'll be, something to look forward to. So, and by the way, don't forget, if this all seems terribly scary, the calculator, when I show you what it can do, will make you breathe easily because it's going to help us with all of this. It's going to make things much, much simpler for us. But we have to understand what's going on behind the scenes before we start leaning on the calculator. All right. So I say it's time to go start our Thanksgiving break. Well, you guys can. I have 5 more classes to do, but you can go have fun and get ready for Thanksgiving, and I'll see you all next Tuesday. So good. Have a nice break.
Thank you.
Well, I see a chat. I didn't see the chat. Oh, thanks. Yes. Okay. That's the problem with chats. I don't always see them right away. Thank you. Bye. Bye, everyone.